The third law of thermodynamics. At absolute zero temperature, the entropy of all homogeneous crystalline condensed substances in a state of equilibrium becomes zero. Mathematically, limit T tends to zero, absolute temperature tends to zero, entropy is equal to zero. Okay, then the principle of increase of entropy. Now, for any process, we can write for the total mass for any process ds greater than or equal to dq by t. This is from the Clausius inequality. If the system is isolated, so dq is equal to 0, so ds for isolated system must be greater than or equal to 0. And for a reversible process, the ds isolation is equal to 0, so it is s is equal to constant for a reversible process. And for irreversible process, ds isolation isolated system greater than 0. Now this is the figure. This is a system. This is a system, and this is the surrounding. This is the boundary of the surrounding as a boundary of the isolated system. Actually, these two together make it universe. Okay. Now, thus, it is proved that the entropy of an isolated system always increases from these two equations, this equation and this equation. It can never decrease. The last two lines, the above lines mentioned above, is called the principle of increase of entropy, or simply entropy principle. And This is the general quantitative statement of the second law of thermodynamics. We can form an isolated system by putting system and surrounding surroundings together. The universe is an isolated system. So universe is equal to system plus surroundings. So ds universe is isolated system, universe greater than or equal to 0 for all possible processes. That means ds system plus ds surrounding, that will be greater than or equal to 0, because universe is broken up into system and surroundings. The entropy may decrease locally at some region within the isolated system, but it will be compensated by a greater increase of entropy somewhere within the system, so that the net effect of an irreversible process will be an increase of entropy of the whole system. Okay, so this is actually principle of increase of entropy. Now this is the example of the increase of entropy of the universe, of the system universe. Now this is a subsystem A. This is a subsystem B, temperature T1 and T2, and the connecting rod C is at temperature T. Now what is this system is giving out the heat, okay, to the rod. So this entropy change is minus Q by T1, and the rod is receiving the Q, so plus Q by T, and this body is receiving the heat, okay, so that is plus Q by T2. Okay, now you see this is the A minus q by T1, which I have told, SB plus q by T2, the C, the rod, minus q plus q by T. Because you see, in the rod, what I told earlier, there are two ends of the rod. In one end, plus q is coming. In the other end, minus q is going to the B. So, plus q minus q by T. Plus q minus q by T. So, this is for the rod. Now, q is equal to q, take q common, is equal to T1 minus T2. Okay, by T1 T2. Now, as T1 is greater than T2, so delta S of the universe greater than 0. Okay, this is the increase of principle of the entropy. Okay. Okay.